Chapter 6 covers discrete probability distributions. So, discrete probability distributions still involve probability. It's similar to what we were doing in Chapter 5. The difference is that in Chapter 6, it's dealing with probabilities for not just one event, but the whole distribution of probabilities for all possible events. And in the first slide of the Chapter 6 slides, there's a histogram, and it doesn't really say what x is, but let's just say that x is going to represent the number of customers waiting at a store at 6 o'clock p.m. So let's say that at this store they have a lot of data and they know how many customers are typically waiting at 6 p.m. and they may have a whole probability distribution. And if that's what x represented, then let's say right here, for the 10, that would stand for 10 customers. And if you go up to where this is, it looks like the probability over here is about 0.06. So you would know that the probability of there being 10 customers waiting is 0.06. But we could know other customers as well. Let's say we want to know the probability that there would be 16 customers waiting at 6 o'clock. So for 16 customers, we'll go up this histogram up to the top of this bar, and it's hard to tell, but I'll just go across, and that's probably around 0.95. I'm sorry, 0.095. So we would say that the probability of there being 16 customers waiting at the store is about 0.095. So that's the idea. You're working with probabilities for every possible value of x. You'll hear the term random variable quite a bit in this chapter and afterwards. And random variable is just a variable. They call it a random variable because it's a variable that's determined by chance. So that would include any variable involved in an experiment. In some experiment, there is random assignment that scientists use, or random selection. So whenever you introduce randomness in your experiment, then you're working with random variables. Another term that comes up in this section is discrete. And discrete just means that your variable has a finite or countable number of values. Usually this means that the value can only be a whole number. Here are some examples of discrete variables versus the opposite, which would be continuous variables. And we want to identify which is which. Let's say in number 6, the time it takes for a light bulb to burn out. we want to think about is that discrete or continuous? And time is continuous because time can have any value. You can have time that's 2 minutes or 2.5 minutes or 2.59 minutes. There's no end to how you can measure time. So time would be continuous. Part B, the weight of a T-bone steak. So weight is also continuous. You can have a steak that weighs 1 pound or 1.2 pounds or 1.33 pounds. You can have any possible value for a weight of something. So that's also continuous. Let's see, the next example, the number of free throw attempts before the first shot is made. When you're counting free throw attempts, those can only be whole numbers. You can attempt 0 or 1 or 2 or 3 free throws, but it wouldn't make sense to say that you attempted 1.753 throws. They can only be a whole number, and so those are discrete. And then the last example, in a random sample of 20 people, the number of people with type A blood. So here the variable is the number of people with type A blood. That would have to be discrete. That number can only be a whole number, 0, 1, 2, 3, 100, 500. But it wouldn't make sense to say that 2.39 people have type A blood. So this is also a discrete variable. So the slides go into quite a bit of detail, and it's good background, but I'm going to jump to some examples. There are some formulas which I'll talk about in the examples. I'm going to skip over those for now. And we'll go to the first example, 6.1, number 17. So in this example, this is involving a sample of households, and the variable was the number of televisions in a household. So there's our variable. And so they did this study, and this is the result they came up with. This is all possible values of x, number of televisions in the households, and these are the probabilities. So, for example, the probability that there would be 2 TVs in a household was 0.261. Part A says verify that this is a discrete probability distribution. The main thing to do to verify that it is a distribution is to add up all those probabilities and make sure that they add up to 1. And I did this earlier, and they do add up to 1 when you check. Part B, draw a probability histogram. These are histograms like what came up in chapter 3. So here's the axes all set up. It'll be good to label these axes. In this case, it's a probability histogram. So y-axis is going to be probability, and then the x-axis is whatever the variable represents. In this case, number of TVs in a household. And for the histogram, we'll make the bars according to this distribution. So 0 TVs had a probability of 0, so there's no bar there. 1 TV had a probability of 0.161. We'll make a bar. .161, so here's 0.1, 0.2, so 0.161 is maybe here. Like that. The next one for 2 TVs, the probability was 0.261. So I'll make a bar that goes up to 0.261. About there. And just continue in that way. 0.176, 0.186. .116, 0.055. .025. The last two are 0.010. That's just barely above the line. There we go. Part C in this question says determine and interpret the mean of the random variable. To find the mean of a distribution of probabilities, there's a particular formula, and this is the formula. I guess this right here in particular. And the formula is to multiply every x value times its probability, and then you add them together. So the first x value is 0, its probability is 0, 0 times 0. The next x value is 1, and you multiply it times its probability. The next x value is 2, you multiply it with its probability. And you do that until you get to the last one, x being 9 times its probability, add them all up, and you get 3.21 televisions.